Assalamualaikum. Good morning, good afternoon, good evening, wherever you are. I like to present our paper on isitia 25 in the 2024 years that have titled Cost-Sensitive Approach for Improving IoT RUC Curve of Software Defect Prediction. On behalf of the author, myself, Rizal Berubahwares, and Islah Khofifah Nuraini, would like to start with an agenda. First, our outline including introduction, background, research question, research methodology, result and discussion, conclusion, and future work. An introduction about software defect prediction. In many startups have failed bankrupt due to a problem with defective software after being launched. It's said by Mark Crown in 2020. Also, the cause of software failure is that the larger and more complex software, more likely is that defect will occur in it, said by Mas Kumar Tohata 2020. The prediction of software can help predict defect before the software is released to the public, also shown by Junhua Ren 2020. Problem in software defect prediction. In reality, when the prediction process is carried out, there are several problems that occur. One of which is the misclassification cost. The misclassification cost is a loss that occurs due to classification error during the prediction process. One of the causes of misclassification is unbalanced class problem. You can see there is unbalanced green, more green than the red one. Problem of class imbalance in machine learning is unavoidable. This is because machines that work automatically only pay attention to the majority class compared to the minority class. In the few peripheral study, the value of predicted accuracy of software defect was unusually focused without considering the misclassification cost that occur in the prediction mode. Cost-sensitive learning is a classification process in which the process pay attention to the data that has been misclassification cost, say by Corano in 2020. To minimize losses from misclassification, we can use cost-sensitive learning method during the prediction model. This is the illustration. As a proof of the use of cost-sensitive learning, a comparison can be made using the performance evaluation AUC and RUC curve as a measuring tool for classification problem in determining the threshold model. In the previous research and the latest research, there have several researchers have doing cost sensitive, including the reference number 11 and using the not an SDP problem using CNN and reference number 12 using INN, reference number 13 using CNN. And our research have doing cost sensitive and using application software defect prediction, and also we use method ANN to machine learning. Our research question has two. Number one, what is the effect of the performance of RUC in if the process classification software defect use a cost sensitive method instead of a cost-insensitive one. The second, several software defect prediction tests that we carry out that algorithm has been the best optimization in the use of cost-sensitive learning based on the performance evaluation.
Okay, in this section we have research methodology, and we can see in this picture the methodology process is carrying out in several stages, starting from dataset gathering, pre-processing, compiling to scenario, and the last being evaluation. We will go over each one individually for more information. Okay, first at this point we gathering the data. We use a NASA dataset which was obtained via online search. The dataset used in open to public and can be found at repository. The data used is that one unbalanced data, so it's susceptible for use in the model that we process. The dataset used in CSV format and has been extracted into collection features and data label. From the NASA dataset, we use 5 datasets selected, namely is PC1, PC2, PC3, CMI, and KC1. KC1 below is an example of the content of NASA dataset as follows. Pre-processing must be done before the dataset is modeled. The first stage of data pre-processing is data cleaning. To correct missing value data, as example can be seen in the picture above. Missing value found in dataset PC1 in row 559, the feature PC1 has no value, which is one of the feature is none. We must fill in the value of the feature here by using the average of the feature in dataset. The data normalization process will change the dataset value to scale of 1 to 0. So the later during the modeling process, the machine will easily study the dataset. In the modeling process, if the dataset used is not good, then the prediction result from the algorithm cannot be relied upon in the future prediction process. And after pre-processing data, we can use neural network and consecutive learning to the data model. We can see in the picture how to implementation of consecutive learning and neural network in data training and data testing. As a comparison of the result between scenario 1 and scenario 2, I use evaluation the performance of the prediction that have we been. The calculation of performance result use the conversion matrix as a performance reference value, and the final performance evaluation we use the result from AUC because I know that we have 5 NASA dataset. The average AUC final value of the 5 dataset is calculated. And we have the final evaluation. Results are focused on using AUC measurement that are suitable for in-class imbalance problem. Below is visualization of the comparison of the AUC value of 5 datasets we use. The result of comparison of 2 scenarios can be seen in figure. The result show that use of causative measure can increase the average AUC value of dataset by 13.6%, and table 3 show the experimental result where the highest result were obtained from PC1 dataset at 85%. And we have a result decision from our Uzi curve. From the Uzi result is each dataset that has been tested in figure 5, 6, 7, and 8. It can be seen the result of compressing of the ROC curve obtained before and after using consecutive method. The blue line using consecutive method and the red line not using a consecutive method. From the result, the curve that close to the value of 1 produce a better model because priority to prediction value is close to the actual value. The final evaluation results are focused on using AUC measurements that are suitable for our case in class imbalance problems. Below is visualization of compression, the AUC value, the dataset, that we use, the result of comparison to scenario can be seen in figure. From the result of comparison the 5 algorithm, the highest average AUC value is found in neural network algorithm, which is obtained the highest AUC value in 4 datasets. Now we have a conclusion is one constructive method can minimize large feature loss caused by misclassification of unbalanced dataset, and result from analysis which was performed on 5 datasets by comparing the performance of the AUC value in each dataset. The result obtained using the consistent method can increase the average of AUC value by up to 13.6%, with the highest increase in PC2 dataset but by up to 20%, and the curve on the ROZ is close to 1. And 3. From the result, the compressing of 5 algorithms, the highest average AUC value is found in neural network that algorithm, which obtain the highest AUC value in 4 datasets.